Okay, the lecture problems for Chapter 9. Take a second to read the problem. We're asked to find the angular acceleration and the angle through which the blade has turned, knowing that we have some blade that is undergoing constant angular acceleration, starting from rest to some angular velocity in 6 seconds. So what we know is we want to know the angle, and we want to know the angular acceleration. We know that the initial angular velocity was equal to 0. We know that the time was equal to 6 seconds, and we know that the angular velocity is 140 radians per second after those 6 seconds. So we can first say, okay, angular velocity is equal to initial angular velocity plus the angular acceleration multiplied by time. So the angular acceleration is going to be angular velocity minus initial angular velocity divided by time. Initial angular velocity is equal to 0, so we're really left with 140 radians per second divided by 6 seconds, and we're going to come up with 23.3 radians per second squared. So there's the angular acceleration. Now we're asked to find the angle. We know that the angle is going to be related to the initial angle plus the initial angular velocity multiplied by time plus 1/2 angular acceleration multiplied by time squared. We can say that that guy is equal to 0. So our angle is going to, and actually this guy is going to be equal to 0 as well. So 1/2 multiplied by the angular acceleration multiplied by the time squared, or 1/2 23.3 radians per second squared multiplied by 6 seconds quantity squared is equal to 419.4 radians. So that's how far it's actually traveled. Just kind of a side note, if we were curious about what the velocity would be at the edge of the wheel, we could say that the velocity is related to the radius multiplied by the angular velocity. In this case, the radius is 0.1 meters, and we could figure out what the linear velocity would be at some point on the wheel for this guy. So take a second to read the problem. Essentially, I'm trying to figure out what the diameter should be of a cylinder that is raising up buckets. I'm kind of drawing a little schematic here. Here I've got my bucket, and it's traveling up with a constant linear velocity of 0.02 meters per second. And I have a wheel that has some radius or some diameter that's double that, and I'm told that this guy is also going to be rotating with an angular velocity of 7.5 RPM, revolutions per minute. I know that there's a relationship between the linear velocity and the angular velocity. It's simply the radius between them. So to pick my radius, I'm going to divide my velocity by my angular velocity, come up with my radius, and solve for my diameter. However, the very first thing I need to do is convert this angular velocity from 7.5 revolutions per minute into something that is more meaningful. Translation, let's convert it to radians. I know that 1 minute is going to have 60 seconds associated with that, and 1 revolution is equal to 2 pi radians. So my angular velocity is also 0.785 radians per second. We can't work any of these problems if it's in revolutions per minute. It's like trying to work in miles for some of this stuff. So now I can simply say that my radius is going to be equal to my linear velocity divided by my angular velocity. So 0.02 meters per second divided by 0.785 radians per second, and I'm left with 0.0255 meters. My diameter is simply going to be double that, so my diameter is going to be 0.059 meters, or 5.9 centimeters. Whichever one suits your fancy. It's a little bit prettier to write 5.9. Now for the second part of the problem, it says suppose you want to now have the bucket accelerating upwards with a linear acceleration of 0.4 meters per second squared. Now, how fast should this guy be turning? Much like we know a relationship between linear velocity and angular velocity, we also know the same for linear acceleration and angular acceleration. So I'm actually not looking for linear velocity, I'm actually looking for angular acceleration here in this part of the problem. That's what I'm solving for. So angular acceleration is simply going to be equal to the linear acceleration divided by the radius, or 0.4 meters per second squared divided by the radius, 0.0255 meters. And at the end of the day, we're going to come up with 15.7 radians per second squared. That's my angular acceleration. Okay, this problem may look a little more complicated, or may look fairly complicated, but if we break it up into pieces, it's not too awful hard. First, we'll use kinematics to solve for the velocity of the block after 2 seconds, and then we'll relate that to the rotational angular velocity of the wheel, and then use work energy to solve for the moment of inertia and hence the mass of the block. So if I have this block initially at some position, it's initially starting from rest, so that's going to be equal to 0. Then after a time of 2 seconds, it's going to be down here, and it's going to have some velocity. And just to make my life simpler, I'm going to say that this is my 0 position, so that's my y 0 position. Therefore, this is going to be 3 meters. We can look at our kinematics equation and decide which one we want to use. I don't use this one very often, relating the change in position to the average velocity of the object. However, in this case, it's particularly nice not to have to solve for acceleration, knowing that it's starting off from rest and finishing at its 0 position. I'm going to solve this guy for the velocity. So the velocity at point y is simply going to be the negative 2 times the initial position divided by the time. So negative 2 multiplied by 3 meters divided by time, or divided by 2 seconds. And I'm going to end up with negative 3 meters per second. All that negative really means is that it's in the downward direction. I can now relate this guy to the angular velocity of the wheel, knowing its radius right there, where I say that the angular velocity of the wheel must be equal to the y velocity divided by the radius, or negative 3 meters per second divided by 0.28 meters, and I'm going to get negative 10.71 radians per second. Again, all the negative is a direction. So I'm just going to move this guy up here, and that way I can clear off some space here and work the next part, in which I'm going to be looking at using the work energy theorem to now solve for the rotational mass of the block. I know that the work energy theorem says that an object's kinetic energy plus the object's potential energy plus any work done from other sources must be equal to the kinetic energy point 2 plus the potential energy at point 2. I know initially that this system was at rest, so it had no kinetic energy. I know that there are no other forces, there's no friction here, so that guy's going to drop out. And lastly, I know that I am finishing at my y is equal to 0 point, so I have 0 potential energy at the end of my motion. So I'm starting off with some initial potential energy here, and that initial potential energy is simply stored in the fact that this mass was originally at some height. So mass times gravity times y naught, that is my initial potential energy. And after it's fallen for 2 seconds, I have two types of kinetic energy. I have the block, which is moving at some velocity which I solved for, which is 3 meters per second, and then I also have some energy that is in the wheel, because the wheel is now rotating, that is 1/2 I omega squared. What I can do is, I know all of these terms, I know all of those terms, I know that. I can solve for the rotational, the moment of inertia of the disk, which after a little bit of algebra is simply going to be 2 multiplied by omega squared, mass times gravity times y naught, minus 1/2 mass velocity squared. It's a simple matter of plugging all of these things in. So 2, I got my omega squared, which is 10.71 right there. I know that the mass of the block was originally 4.2 kilograms. I know gravity, of course, 9.8. Y naught is going to be 3 meters minus 1/2 mass, and mass 1/2 4.2, and I erased it, but the initial or the velocity of the block is going to be 3. Square all that stuff, and I'm going to come out with I being equal to 1.824 kilograms meters squared is the unit for moment of inertia. So I've been told to treat that pulley as a uniform disk. I can go ahead and I can look up what that is in the book. It says that the moment of inertia of a uniform disk is going to be the mass of the disk multiplied by the radius of the disk, and there's a 1/2 in there that I almost forgot. I'm interested in this mass of the pulley, and I know the radius, so the mass of the pulley is going to be 2 multiplied by the rotational moment of inertia, and I forgot a squared right up here, so divide that guy by the radius squared, and I'm going to say, okay, this is going to be 2, 1.824 is my moment of inertia. The radius of my disk is 0.28, and that guy is going to be squared, and I end up with the mass of my disk coming out to be 46.5 kilograms. So there we have it. We've taken a complicated problem and broken it up into several pieces and solved for the mass of the disk.